Syzygy, episode 109, Something from Nothing. And welcome back to another edition of the Syzygy podcast. My name is Chris Stewart, sitting as usual around the round table in her office. Dr. Emily Brunsden, how are you doing?
Hello. I'm well, thank you.
Good. We're recording this on Tuesday, the 6th of June, which you have told me is a very important day in your memory. You remember this one. Why is that? What happened on the 6th of June?
Well, the 6th of June 2012 happens to be one of the few dates of my life where I can look back and I can tell you exactly what the weather was on that day.
6th of June 2012, that's like 11 years ago, and you know what the weather was. So something happened. I'm guessing it's astronomical.
Oh, yes.
Yeah, okay. Because weather-related, I'm guessing that the outcome wasn't great.
No,
what happened
case.
on the 6th of June 2012?
So we had the transit of Venus.
Right, yes, I do remember that, yeah.
So Venus passed in between the Earth and the Sun.
Yeah, that's not usually something which is interrupted by the weather, though.
Well, the actual transit happened.
It's going to happen regardless, yeah.
Yeah, but it was a lovely transit. It was visible from many places in the Southern Hemisphere. I was in Christchurch in New Zealand at the time. And it was just one of these very rare events. So you often see in the media, this is the last time you're going to see a moon this particular size for whatever. It doesn't mean anything, right? The moon's just the moon.
We had one of those the other day. My daughter said to me, "Dad, what's a strawberry moon?" It's like, it's literally nothing. Darling, don't worry about it. It's probably the first full moon in June. So let's go with that.
Yeah.
Yeah.
No, but this transit of Venus is actually one of these rare events.
Yeah, that's actually a thing.
Yeah. So, and we're not going to see another one, I think, for another 70 odd years or something like that.
Wow. Okay.
So it was kind of my last shot, at least, to
so
see
you
this
really
thing.
wanted to see this one.
Yeah. So it's a big deal. We, at the University of Canterbury at the time, I worked with the outreach team and we put together this big program. We had school kids coming in on buses to come to lecture theatres. We had solar telescopes getting set up so people could look. We had a live link down to the observatory at Mount John. It was exciting. It was a great
Sounds
thing.
great. Good day, was it?
It snowed.
Okay, that's not just bad weather. Normally, right, if it snowed, like that would be exciting. Do you get much snow in Christchurch?
Not very often, no.
Not a lot.
You're lucky if you get it once a year,
Right,
really.
so that would be exciting. This would be great,
Well,
fantastic.
yeah.
Except for the fact that we wanted to actually be looking at something else.
Yeah, so the buses couldn't bring the kids in. Yeah, we couldn't sit. Well, it's 0 point pointing at a solar telescope at a cloud of snow, isn't there?
It's a very difficult thing to put down on the risk assessment as well. What if it snows? Well, I guess we all go home then.
Yeah.
Yeah. Okay. Well, I'm sorry about that, but it's not snowing today here in York, but that's all right because we don't need to look up anyway.
No.
Instead, today we are going to be. We're actually basing the entire episode today around a listener question. We had an email through our website, syzygy.fm. If you feel like throwing us a question, you can do exactly the same as listener Eve Sproats. Eve, I hope I've got your name right there, who wrote to us last week and said the subject of the email was how much energy in the universe? Hi, Emily and Chris. First of all, I just wanted to say thanks for making such a fabulous podcast. Well, you're very welcome. I just had to throw that one in.
Lovely.
Really enjoyed the most recent episode, Biggest Bang Ever Part 2. You mentioned the boat being the Big Bang, right? The biggest or the brightest of all time being the Big Bang, right? And it's harder to get more boaty than the big one.
It's the biggest
than the Big
boat.
Bang. And led me to wonder, she says, how much total energy is there in the universe? I know it must be conserved, so it can't be created or destroyed. But does that mean that there's a fixed number of joules of energy? And do we know what that is? How much is there? Can we find out? Emily, do we know how much energy there is in the universe? That's the episode for today.
Yeah. That's a brilliant question.
It's a really good question, and it's one that did make the both of us just sort of sit back a little bit and go, that's not simple. So we're doing an entire episode on that today. Emily, where do we begin? How much energy? And are we going to include in this the whole Einsteinian concept of energy is all the stuff? It's
absolutely.
Mass, matter, particles, radiation, it's all the same stuff.
We've got to go everywhere with this,
okay,
right?
Good.
Do the biggest thing.
All right, kick us off then.
So I'm clearly going to do the astronomical approach to this question, right? So Chris may have different opinions, theories /
other approaches
research.
are available.
Yeah,
yes.
that he'll bring in later. But let's start with the astronomical approach.
Let's do that.
But I'm going to actually start with the philosophical approach before we get here. And that's going to break the question down.
Okay, good.
So what is the energy of the universe? We're going to have to look at what is energy, first of all. What is universe? That's also quite important. And there's a third.
What do the words how, much, and is mean?
Yeah. And definitely, when are we talking about? Because that turns out to be an important question as well.
So, as we mentioned, this is not a trivial question. We need to define all the things before we can even begin to think about what the answer might be. Okay. Kick us off.
So let's start with what is energy. So we as physicists, as astronomers, understand energy to be kind of what is it? I don't want to do this philosophically.
What is energy?
I don't want to do that.
What is energy? I mean, Feynman is quite famous. Richard Feynman, the great theoretical physicist, who also did an extraordinary job of pulling apart concepts of physics and cosmology and explaining them in. I was about to say in simple terms. That's not strictly true, but in understandable terms. And he always talked about energy as being energy is accounting, right? We have ways of measuring what's going on around us in the universe, measuring what things do. Cars driving along the road, balls rolling downhill, light zooming its way across space from the sun and so on. And in order to describe what those things are doing, we find that there are certain things that we can calculate which are really useful. And those things can be sort of collectively termed as different kinds of energy. But I mean, what is it? It's, to Feynman, it's a way of keeping track of what's going on. But is it actually stuff? That's where it becomes complicated.
Yeah, well, that's actually a pretty good, first jumping off point.
Yeah, it's accounting.
If we convert that sort of concept into astronomy, then the things that are energy that matter, at least in the universe, well, first of all, we got photons. Photons are energy, or they have energy, or radiation, if you want to talk about sort of collectively photons. So we talk about photons having a particular energy. You have high energy photons like ultraviolet X-ray photons. You have low energy photons like radio photons, and kind of the middle stuff are the ones that we see, the optical ones.
Yeah, it's worth pausing at that point, just to sort of put a little box around some of that philosophical stuff. When we say photons have energy, like but what does that mean? Like the mental image is almost this glowing thing coming through the universe. But it is it's a photon. It is light, so you can't really think of light as glowing. That's a bit weird. When we say something like a photon has energy and has a certain amount of energy, lots of energy, small amount of energy, that's in relation to what can it do when it hits something, when it gets absorbed by something. And the energy embodied with a photon, with a particle of light, can be transferred to something else to make it do something. For example, if it hits a solar panel, it can be converted into a different kind of energy, which makes electrons flow in a circuit, that kind of thing. So it's that accounting idea of how much of this number, which we'll call energy, does this photon have? Large amounts of energy, small amounts of energy. And we can calculate that really, really carefully. It all adds up. But it's very difficult to answer. What is it? What is this thing?
Yeah. So, let's say the radiation or the photons carry some energy. Now, I led with this because it's actually very, very small in terms of the overall energy that we see in the universe.
Yeah.
At least in today's universe.
Not a lot. Yeah.
Some estimates are kind of around the 0.01% or probably less.
So you're saying of all of the photons?
Of all the energy in the universe, the photons and the radiation make up 0.01% or less.
That's not a lot. When you consider it, like it feels like there's quite a lot of it. You look at the sun. Don't look at the sun. That's a bad thing to do. But if you were to, look at how much energy is coming off the sun, it seems like quite a lot. And we depend on, that's where almost all of our energy on Earth comes from. Ultimately, is from the sun. It feels like there's a lot of that, but turns out no. It's a rounding error.
Yeah, it's completely ignorable in the context of what we're going to do today. So that's why I wanted to start with that. Let's get rid of that. We're just going to ignore it from now on.
Thank you, photons. Right. You've done your work.
So the next one you might want to think about is mass. And we talk about mass and energy being kind of an equivalent thing because we can exchange mass and energy. So you can turn mass into energy, you can turn energy into mass. Yeah,
this is the whole E equals MC squared thing that Albert Einstein is just, so famous for. And it's it's more than just this amount of mass is equivalent to this amount of energy. Like you literally can and routinely do turn one into another.
Yeah, exactly. Well, the sun's doing it all the time, for example.
Right? Right. Nuclear reactions are doing this all the time. And even to a certain degree, chemistry does. You know, when you're combining atoms together to make different kinds of chemical molecules and so on, the very small differences in the amount of energy that the different atoms and the different molecules have in configuring themselves in different ways become different kinds of energy. You know, it's you can see it, you can do it.
Yeah. So now this is where you might have expected this question to start off with, by thinking, okay, so we've got some mass in the universe. That's very obvious, right? We have planets that we like to
I'm
live
looking
on.
at some right now.
Yep.
You know,
Some, many of them.
quite a lot in this office. There's a lot of mass here.
Planets. So we have all the obviously the atoms that are on planets, but planets, stars, galaxies, gas, dust, whatever, all the stuff that's in the universe, right?
It's kind of the most obvious and familiar kind of energy that we know of because we are it.
Yeah. Now, if you were to sort of we live in a very energy or in a very mass dense environment being here on planet Earth, right? So there's a lot of matter around us compared to, say, the huge voids of empty space which exist elsewhere.
Right. Yeah. I mean, we talked about this a while ago. And, I know it's come up on a few different podcasts of, space is completely empty, right? It's a vacuum. No, it turns out, no, there's stuff in space. We talked, was it last week, about, a shockwave from a supernova reaching us. So shockwave through what? Well, through the interstellar vacuum, right? And it's not a vacuum. It's got stuff in it, enough to be able to carry a shockwave. It's not empty. It's a hell of a lot emptier than this room.
Yeah. So you have different, I guess, classes of empty as well. You have the space between, say, the planets and the solar system. That's empty, but not particularly empty. There's stuff there. Then you have the space between stars. That's a bit emptier again. Then you have the space between galaxies, and that's really quite empty. So there's
hardly anything in that at all.
Yeah. And then you have these structures in the larger universe called voids, which are really, really, really empty. So, yeah.
Yeah. But not actually empty. But anyway.
But very little. Very little stuff. So what we're going to do is take all the mass and just kind of smooth it out, because if just counting stars and planets and galaxies kind of gets hard. So what we do is we talk about the density of matter.
Okay.
So we smooth it all out and just pretend it's equal, which on the very, very largest scales of cosmic structure is a good assumption.
Yeah. I mean, a nice illustration of that is, we've talked a few times on the podcast over the years about the cosmic microwave background, right? Where you look at the wash of background energy across the universe. And the thing that the physicists and the cosmologists focus on are, if you go and Google that phrase, cosmic microwave background, you'll see these really bumpy pictures of the universe, the sky, which are filled with little bumps. And that's the bit that we focus on, ignoring the fact that those bumps are tiny. And actually, the wash of radiation across the universe, this background, is almost completely uniform. It's almost exactly the same in every single direction we look.
Yeah. And so you can kind of make the same assumption really about matter. It doesn't, in some cases, it doesn't really matter the fact that you've got clumps of matter. I'm using matter in too many different senses.
We live
now.
on an anomaly here, that we live on a particularly clumpy clump. Yep. But generally speaking, what you're saying is we can just wash those clumps away, and we've just got matter spread evenly through the universe to a good approximation.
Yeah.
Okay, so if we do that.
So you end up with a density of something like 4.5 times 10 to the minus 28 kilograms per meter cubed.
Okay, so let's just think about that. Per meter cubed, you can think about that, right? A meter, put your arms out, that's a couple of meters. So, meter by meter by meter. And 10 to what? 10 to the
minus 28.
That's not a lot. It's very little.
It's more or less a proton.
There's one proton in a large cardboard box.
Yeah.
On average.
On average in the universe. So one hydrogen nucleus.
That's insane. That's that's like a hydrogen atom in a big packing crate.
Yeah.
That's madness.
So that's the average density of let's put the prefix here that's going to give you a clue of ordinary matter.
Ordinary matter, okay.
In the universe.
Right. Yeah.
Okay.
All right.
So that's the
Yeah.
stars, the atoms,
Yeah.
galaxies, all the stuff that we know and love is what we would call mass on an everyday
That
basis.
really does point out, doesn't it, that even though we are focused on the planety bits and the starry bits and the galaxy bits and even the clustery bits, actually the universe is basically empty. There's not a lot of stuff in it.
No.
Yep.
So let's go to the next part. So I said ordinary matter. What's the not ordinary matter?
Yeah.
It's, of course, the dark matter.
Dark matter. This has come up recently. We talked a bit about it. Yeah.
So this is...
And there's a lot more of that.
Oh,
we
yeah.
think.
Yeah, there's about 5 times more dark matter than there is ordinary matter.
Mm-hmm.
So if we don't really know what dark matter is, but we're fairly good at understanding what it does.
Sure. Yeah.
So-
we see its effect. We see its gravitational effect. We know that there's something there. And there are loads of theories around about what that might be. But no one's actually definitively said, no, I've seen it. I've got it. Got some here in a jar. This is what it is.
Yeah.
And so
So it
jury's out
behaves
on
a
that.
lot like ordinary matter that we know and love. It just doesn't seem to want to interact with photons. And that's
Yeah. I mean,
okay. That's a choice.
that's a perfectly valid lifestyle choice. And that's the dark part, right? It's dark. We can't see it in the sense that it doesn't interact with the electromagnetic field with light, but it definitely does through gravity because that's the whole point. We
So it
know
behaves
it's
well
there.
with gravity.
Sure. And so let's assume that it is a thing and it is there.
Yep.
There's 5 times more of that than the visible matter.
Roughly, yeah.
So that's like 5 hydrogen atoms worth of dark matter within this large packing crate.
Yeah. So, I mean, it's a rounding error, but if you put all the ordinary matter and the dark matter together, you get about 5 protons in your box.
Yeah.
Right?
Which is still not a lot, can I just point out?
No, there's not many. Not many.
Because those things are really small.
Now, so altogether, that's all the stuff that behaves nicely with gravity. Mm-hmm. And so I'm going to take this a little bit sideways in our calculation here. So we've got a density of all the matter that behaves with gravity. Now that's important. That number is actually really, really important. It's something called the critical energy density of the universe.
Right.
So there is a number that exists that's called the critical energy density, and it turns out that the observations that we make seem to be almost exactly the same. Mm-hmm. So the critical energy density is, we imagine that we've got gravity which is trying to pull all the matter together in the universe, right? So you have in space and with the absence of any other gravitational fields, you put 2 pieces of matter together, they'll have a gravitational attraction, they'll move towards each other.
Right. That's what gravity does.
Yeah. So the whole universe does that on the grandest scale, right? All the galaxies are attracted to each other gravitationally, for example. So the critical density is asking the question, with gravity and all this matter, what is the density of matter you need for the universe to be perfectly balanced?
Right.
So if we're expanding out currently from the Big Bang, the universe is expanding, what is the amount of matter or the density of matter in the universe such that that expansion gets slowed down by gravity till it just gently comes to a nice little stop?
Okay. And this is a hypothetical at the moment because, I mean, I guess we'll come to in a second, like, is that what we're doing? Is that what we're doing at the moment? Are we on that critical edge? But we can come to that in a second. Let's just hypothetically say we have a universe.
Yeah.
It went kablooey 13.8 billion years ago or whatever it is for reasons unknown as yet. But it did that, expanding ever since. And so, like a car coasting along the road with its engine, turn the engine off, it's just going to slowly come to a halt. That's the idea here.
Yeah.
We're expanding and gravity's pulling back. And so the critical density is how much mass do you need for that to just reach zero over an infinite amount of time? It just drifts to a stop. As opposed to too much mass, too much energy in the universe where it expands and then it clumps back together again. The gravity takes over and it goes, no, come back. And everything crushes back again in a big crunch. Mm-hmm. Or what? What's the other side of the critical density?
Or the opposite is that the gravity is not strong enough, so the universe just keeps on expanding forever and ever and ever.
Right. Not that it speeds up, but that it just keeps coasting on.
Yeah, exactly.
In the sense of the car going along the road, it's like there's no friction.
Yeah.
It just keeps going forever.
Yeah. So gravity's not strong enough to overcome that.
Okay.
Yeah. So the critical energy density, if you do your sums and look at the cosmological models, turns out to be this 5 protons per cubic meter.
Right. Which is what we've got. Right.
So we are struggling, we collectively are really struggling to say, have we got more than 5 photons per cubic meter? Have we got fewer? It's really hard to measure.
We're right on that edge.
We're right on this boundary. So basically, it seems for all measurements that we've got, we're pretty much bang on this critical energy density.
Yeah, which, like, given all of the possible ways that could have gone, again, we sort of come back to that, like, why would we be special? Why would there be exactly that amount? But anyway.
Feels a little bit coincidental, doesn't it?
Yeah.
But anyway, maybe it's just our measurements aren't precise enough yet.
It could be. Yeah, it could just be that we're close to it, which wouldn't be surprising. It'd just be that's where we are. But being exactly on it would be weird.
Or maybe there's some other piece of physics that we don't understand
Well, maybe
yet.
there is. Maybe there's a deeper reason why.
Anyway, we've got our 5 protons per cubic meter. So from that, we know that's our density. Now you can get to you can then calculate basically what the entire mass is of the universe. But we're going to sidetrack again and answer the second question that I pulled out from this original question, which is we talked about what is energy. The second part is what is universe.
Yeah, okay. Second part of the definition.
If you're going to say, well, that's the density, that's per cubic meter, and you want to say, well, how many cubic meters do we have? You got to figure out how big the universe is.
How big's the universe? And that's not a simple question.
It's really not. There's a short answer and there's a long answer. The short answer is there's the observable universe.
Sure.
So how much universe we can see. Now that is some chunk of the universe which we're in, which is about 46 billion light years across.
And we encountered that a few episodes ago because that seems counterintuitive because the universe is only 13.8 billion years old. So how could we see something which is considerably bigger than that in light years? But the answer to that is that, well, it hasn't always been that big. It used to be much smaller, and the light's been traveling towards us.
Yeah, and the universe has been growing.
Yeah.
So the expansion of the universe.
Yeah. So it's all possible. Go and listen to that episode.
Yeah. So that's the amount of universe we can see. That's the amount of universe we get information from currently.
Sure. It does kind of imply, though, that there might be bits that we can't see.
Well, there are, because every second that ticks by, a little bit of universe goes beyond our horizon of what we can see. Yeah,
which is kind of a weird thought, isn't it? Gone forever, literally.
So a bit scary. Anyway, so the short answer to the question then is you can take that size of the universe, your 46 billion light years across. You can say the universe has a density of 5 protons per cubic meter. You can multiply your density by your volume and you get the mass. And that number comes out to be something like 10 to the 54 kilograms.
Right, which is a big number.
Big number.
That's a
lots
lot.
of kilograms.
Yeah.
Or you can convert that to an energy using Einstein's E equals mc squared, which gives you 10 to the 70 joules.
Even bigger number. So 10 to the 70 joules, and that's in the observable universe.
Yeah.
Okay, well, there you go, Eve. There's your answer. That's how much energy there is in the universe. 10 to the 70 joules, end of story.
Solved.
Yep.
There's a few asterisks.
Asterisk number 1 may not be end of story. Yeah.
Okay, that's the observable universe. Okay, so that's a fairly good number for the amount of energy that's in the form of dark matter and ordinary matter in the observable universe.
Sure.
You can ask the question, well, how big is the actual universe? Not just the bit we can observe.
Sure.
We've got no idea.
Yeah. I mean, by definition, we've got no idea. You could, come up with hypotheses. There are loads of cosmologists out there, theoretical cosmologists, looking at it and going, well, what if it was this? But we can't know because we can't see it.
Well, you've got to answer a very fundamental question first, which is the universe finite or infinite?
Well, exactly. Yeah. I mean, if it was infinite, that would be easy. It's just infinite.
Yeah.
We can see the bit we can see and then it goes on forever. Yeah. But
that breaks your mind quite quickly, doesn't it?
It literally does. It literally does. I mean, the first mind-breaking part of that is, but how do you get an infinite universe out of a Big Bang that was an infinitely small dot? But let's not lose sleep over that today. The more important question is, could we ever know whether
No.
or not the universe is finite or infinite?
No, we can't, because we can't see it. We can't get any information. Information can only travel as fast as the speed of light. We're pooched. That's
Yeah.
it. We can't.
I mean, I guess it's conceivable that there are other ways, that there are more fundamental ways, and looking at things like the curvature of the universe, the curvature of space-time. But even then, I'm not aware of any really good ways to determine whether or not the universe as a whole is this or that, that are certainly testable. So yeah, I'm not sure whether or not there's anything that I've missed. I could go and do some homework, but as far as I know, that's unknowable at this point.
No. So that's a kind of a little asterisk that we'll put there.
Yeah.
There's another big asterisk to put there, which is that it turns out we don't just have baryonic matter, ordinary matter. We don't just have that and dark matter.
Dark matter. Yeah.
We've got another form of energy, which is the elephant in the room,
Yeah.
which is dark energy.
Dark energy. This is the one that came up with all of the observations of supernovae, right? Back in the 90s?
97,
This was
I think,
discovered.
the
There were
paper
some observational studies which were looking at the supernovae and looking at that as a distance scale across the universe, and actually trying to measure the expansion of the universe on the assumption that it was either just coasting along at that critical level, or probably slowing down,
Well,
as gravity pulls it together. And it turns out that's not what they saw.
No,
What
they saw the accelerated expansion of the universe.
Right.
So the expansion of the universe was speeding up.
Yeah, that's not what you expect.
Yeah.
That really came out of the blue, because if gravity is pulling everything together, at most, if we were right on that or just beyond that critical density, you might see the universe coasting along at constant speed, maybe. But speeding up,
Yeah.
that's like that. There's something causing that. There's an action there. And it's not that it's, someone's grabbing this galaxy and that galaxy and pushing them apart in that sense. It's that the idea is that the space-time itself is expanding and accelerating. Like it's speeding up, more and more being created every instant. How the hell does that work? Where does that come from?
No, nobody knows. So I think probably the one of the most straightforward ways to think about dark energy is it's an extra force. It's a pressure that's pushing matter apart. We don't know why. We don't know what does it. We don't know why it suddenly appeared somewhere around 3, maybe 4 billion years ago. It wasn't certainly in the very early universe for reasons we don't know.
Yeah,
there's a lot of don't knows.
If it was there, it wasn't dominating, certainly. Yeah.
No. So, yeah, that's a tricky one.
Really weird. And it's called dark energy, as you say, because it's, we're no idea, literally no idea what it is. It's really hard to even pose the question, what is it? But it is some kind of, force or process. And it has an energetic impact on the universe. It is putting energy into the universe.
Huge amounts.
And huge amounts. Again, this isn't a rounding error. This isn't like photons where it's like we could pretty much ignore electromagnetism. This is big.
It's huge, yeah.
Like how big?
Well, if you add up all the energy now in our energy budget of the universe, we have our ordinary matter that comes out at something like 4.6.
Yeah, we're not so special, really, are we?
No, that's
These
very
planety
sensitive.
rocky bits.
The dark matter, that was about 4 or 5 times. That's 23%.
Okay.
So that gives you 72% more or less of the universe's energy is dark energy.
It's not a good look, is it?
No.
Really, that 73%, and then add on the dark matter, which we still haven't nutted out yet. You're up to over 95% of the universe that we don't actually know what it is, Emily. I'm not holding you personally responsible. I'm just saying it's not a good look.
And we're not that great on the 4.6%, let's be honest either. So.
I mean, that's the easy one. That's the low-hanging fruit.
Well, yeah. So, we're working on it.
Yeah. But then again, you've only had half-decent telescopes for 100 years or so. So, I'll give you time.
Yeah. So best estimates, if you convert that to a density, is it ends up being something like 7 times 10 to the minus 27 kilograms per meter cubed. It doesn't make sense because it's not a matter, piece of matter.
Yeah,
but
if you were to make that equivalent.
So it's a little bit less than the density of the the critical density.
Right.
So it's a bit less than that, but
Okay.
it's energy. So it's perhaps not the greatest number to compare anyway, because we're not talking about matter converting to energy. It's just dark energy itself.
But the point is, there's a lot of it.
Yes.
Yeah.
Yeah, exactly. So that stuffs up your critical density completely.
It does rather.
Yeah. So you had this lovely balance where you just had gravity, mass, Big Bang, whatever. Cool.
Everything was looking nice and simple, if somewhat perplexing. Like, why would it be that way? And then dark energy comes in and goes, hold my beer. I'm going to just completely mess you up with this one.
Yeah. So dark energy has an effect on obviously the ultimate fate of the universe, depending on how strong it is. So if it gets stronger and it starts pushing harder, let's say, it's going to push the universe apart quicker.
Yep.
So that's
And if that keeps accelerating, I mean, they talk about things like the Big Rip, where it just speeds up and speeds up and speeds up until eventually it just tears everything apart. Space-time is expanding so quickly and accelerating so quickly. Not even atoms can stay together anymore.
Yeah.
There's a very long way in the future, but it could be.
Could be. Or it could just die out and go away.
I mean, it seemed to come from nowhere. Could just go, oh, sorry, didn't mean to do that. Oops.
Yeah. I'll just go over here now.
Forgot to turn that switch off. Sorry.
So, that just adds huge question marks now to your sums about what's going to happen to the universe.
Does rather. So where is this pointing us, Emily? Like, the original question was a really simple one.
Yes.
I kind of feel like we're losing grip on this really simple question, which was, hey, Chris and Emily, how much energy is there in the universe? And our answer seems to be...
Well, we can answer that question for at least the amount of energy that comes from baryonic matter and dark matter.
Baryonic matter being the matter that we're familiar with.
Stuff. Ordinary matter, dark matter in the observable universe. And here comes the last bit that I mentioned before. Now.
Yes. Sorry, everyone.
Yes. When does matter? When matters in the universe? Because everything's changing. As we said, the dark energy didn't used to be around. Now it seems to be pretty, dominating. Dark matter does weird things with the expansion of space-time. So density-wise, if you take your ordinary matter, right, let's say you've expanded your universe, which means you've doubled your volume. So therefore, your density goes down by half, right? Because you've now spread out those same few protons over a bigger volume. Then dark matter doesn't do that. Dark matter appears to have some kind of uniform density. So if you double your volume, you still have the same number of particles per meter cubed.
Okay, that's weird.
Yeah.
That's weird. I mean, so much of what I've heard and read about dark matter is still, we think it's still like stuff. Like we think it's still particles, like we know particles kind of to be. And that doesn't sound like stuff that we know,
no,
right?
It doesn't, because particles can come out of energy.
Okay.
So it's a bit confusing. So if that is the case, and dark matter does behave like that, with the expansion of the universe, then of course, as the universe gets bigger, the amount of energy from dark matter will increase over time as more dark matter comes in.
Yeah.
But
okay, all right. So here's a preliminary answer to the question: how much energy is in the observable universe? Now, in terms of common or garden variety, as you say, baryonic matter that we know, and all of the radiation, the electromagnetic energy, bit of a rounding error, but let's throw that in there as well. All the photons and so on, and all the dark matter. Whatever that is, but we can see its gravitational effect. All of that now in the observable universe is
10 to the 70.
10 to the 70 joules of energy. And it doesn't really matter what the unit of that is, because 10 to the 70 is a really big number. And so choose your favorite unit. It's still quite a large amount.
I tried to convert this to something that you could get your head around.
No, you can't.
Well,
one followed by 70 zeros is beyond mortal comprehension.
Doesn't work. But if it helps, it probably doesn't. But we
talked
about the goat a couple of episodes ago.
Yes,
that was that big explosion that came from the huge clump of matter that went into the black hole.
Goats on boats.
Yep. That was 10 to the 46 joules.
10 to the 46 joules. Okay, so it's like 1.5. A bit over 1.5 of those.
No.
That's not right. No, it's not. It's
No.
that's me.
Powers
making
of 10 don't work like that.
Powers of 10. That's me making dumbest error. It's almost that.
That
squared.
times 10, times
Yeah,
10,
yeah.
times 10,
Yeah.
times 10, times 10, and do that about 40-something times.
It's a lot of
30
those.
times, yeah.
Right. So this is, it's a lot. It's to the point where that hugest, goatest boat of an explosion is literally nothing in comparison to all of the stuff.
Which is what you'd expect, right?
Yeah.
Even a big explosion in the universe is not going to be significant in terms of the energy sum of the universe.
Yeah. Which just goes to show that the boat really is the Big Bang, right? That it's we're talking about quantities of stuff in the broadest sense of the term, which are just off the scale of comprehension. Even the biggest thing that we can look at and go, that thing there, how big is that? This big explosion, the biggest of all time, the biggest that it might ever be, is still absolute rounding error to the rest of stuff.
Yep.
Which is pretty awesome. Okay, well, there's an answer.
Yeah, so I've done my sums. That's it.
Well
Solved
done.
the problem.
So
I'll submit my work for marking now.
excellent. Now I'm going to wade in with another really big asterisk, which is from you're the astronomer in this podcast. My distant background is in particle physics, and I left that behind the best part of 23 years ago, but I still like to try to vaguely keep up with things. And I'm going to throw in a large asterisk, which is I think you're wrong. I don't think the amount of energy in the universe is 10 to the 70 joules. I think it's somewhat smaller than that.
Oh, no.
In fact, there's fairly strong arguments to say that it might actually be exactly 0.
Ah.
Which is weird, but also a really nice number to deal with, right? It's much easier to wrap your head
This
around.
sounds
than
like
10
you've been
to the
talking to
70.
theoretical physicists again.
Yeah,
Chris.
there might have been a few cosmologists and theoretical physicists involved here. In fact, most of the ones that you've probably heard of have come up in this particular line of work. If you think of any great theoretical physicists and great cosmologists working in the theory side of things, they'll be in here somewhere. But the whole idea is this. Look, we talked about gravity pulling things together, right? And so here's how to think about how 0 might make sense, right? If you take two objects, they are gravitationally attracted to each other. Yeah, they will pull together.
Yep.
You can even do this as an experiment in undergrad physics labs. If you set up things really, really carefully, it's called the Cavendish experiment. You can measure the tiny, tiny, tiny gravitational attraction between two, say, kilogram-sized balls on a really, really fine torsional pendulum. Right? You can do it in the lab. It's there. It's real. But it's attractive. It's always attractive, which means if you grab those two things and pull them apart, you've got to do work to do that. You've got to put energy in to do that, right? You're putting energy in to pull them apart, which means that when gravity pulls them back together, the energy is going the other way. The gravity is doing a negative amount of energy. It's putting a negative amount of energy into that system. Now, this is where we sort of come to that whole accounting thing is energy goes up, energy goes down. And when you study physics in high school and at university, we deal with this by saying things like gravity or even like positive and negative charges they attract and repel, right?
Yeah.
We can say, well, look, it doesn't really matter where you set your 0 to be, right? A ball rolling down a hill will be increasing in speed, so it's gaining speed energy, right? Kinetic energy.
Yeah.
And the amount of gravitational, what we call gravitational potential energy, is going down as it goes down that hill. And the two balance out, right? It starts with no energy at the top and it's moving quickly at the bottom. So it's got kinetic energy, but it's lost gravitational potential energy. And the two cancel out and you've got 0 again. But that says, well, let's assume that the energy is 0 at the top of the hill. Doesn't really matter in those calculations where you set the 0
You
to
could have
be.
said it at the bottom of the hill.
Right, exactly. And so physicists just get used to saying it doesn't matter, because it's just relative difference, right? And we get used to doing that. But then the cosmologists get involved and go, yeah, but when the universe began, right, what if there was nothing? What if there was 0? And somehow something came into being, we borrowed a bit of energy to make some matter, and We'll worry in a minute about how that might happen. Just put a big
quantum particles
put
do
a
it all
big
the time.
asterisk
They
next
borrow
to
energy
that.
from
Well,
the future.
We'll come back to that
just
one.
naughty like that, aren't they?
But let's say we make something, a couple of particles, a tiny universe. That's got positive energy because it's stuff.
Mm-hmm.
But all of that stuff has got gravitational attraction to everything else, which is negative energy.
Mm.
Total energy, 0. Then play that forward in what has now conveniently become time, because before that, remember, there wasn't even space-time. Because space and time are part of the universe. They're tied into all of this. And so now moving this forward in space-time, that huge explosion expands. Amount of gravitational energy in total remains the same as the amount of other stuff in the universe, and the total energy of everything remains 0. And so you can do calculations which suggest that this is a plausible idea for the universe that we're in. Now, that sounds really, really simple in a sense. It's sort of, well, it's the same as a ball going down a hill, right? You've got 0 energy at the top, and then down the bottom, you've got lots of kinetic energy, and the gravitational energy is negative. It's the same idea. Easy. Why did that take so long? Turns out it's not quite that simple. That doing calculations about the universe is actually complicated.
Yeah.
You know?
And I think although it sort of nicely wraps up a sort of a fundamental question which would come if you came along with my answer and said you got your 10 to the 70 joules of energy.
Yep.
There's this fundamental law of energy conservation, which you learn the first time you sort of encounter physics as a discipline, and it's saying energy is conserved. Just like your ball, your kinetic energy is converted to gravitational potential energy and back again, right? But the total amount of energy in the system is exactly the same, no matter what form that energy is in.
That's the idea.
So one can say, well, this 10 to the 70 joules of energy that's in this particular form now, clearly it hasn't always been in that form. It wasn't in that form at the Big Bang, but what was it at the Big Bang?
Yeah, there are so many places where things get really, really complicated. So let's wind back the clock to the very beginning in a minute. But I just wanted to draw a little line under this notion of, it's a very simple idea of the total energy of the universe is actually 0. There we are. Quick, everyone get photos. That's a great idea, right? We've solved it. But the greatest minds in physics across the last 100 years, from Einstein through George Gamow, through Hawking, and Richard Feynman, they've all worked on this. It's not the trivial idea of it's like a ball rolling down a hill. You've got to look at the really complicated mathematical models in general relativity and particle physics of universes which may or may not be rotating, and rotating messes things up. And what's the shape of the universe? And does this even make sense? And how do you add up all the energy anyway? And what even is this stuff? And when you get there, it's only in the last 10 years that physics has managed to get to the point where we're pretty comfortable with the theories that we've got about the universe actually being consistent with, no, it really could be 0. That's more than just an idea. That's actually possible, built into the theories themselves. It's all consistent. What you don't want is all the mathematics to then fall apart as soon as you put in a 0.
Yeah.
And it
don't
doesn't
divide by
seem
it.
to. Yeah, definitely don't divide by it, although Richard Feynman did that a lot. But anyway, the point is that there's I would say the majority of cosmologists now would say, yeah, that seems like a decent idea. It's not just that it might be 0. It's that kind of makes sense with the whole notion of a Big Bang. But then you've got to wind the clock back to the Big Bang and go, well, what even was there? What was there at the time? And that's where things get really, really slippery, to the point where, Hawking talked about this in A Brief History of Time. Is what do they call it? The bestseller that no one ever read. It's on so many people's bookshelves. Wow, that's really dense. But he came up with this idea that as you go back towards the event of the Big Bang, there's this very uncomfortable moment where you go, yeah, but what's at that point? That, the singularity, as it's called, when everything is so infinitely densely together. What is that? And Hawking and plenty of contemporaries kind of sidestep around it by going, it gets really fuzzy back there. And maybe instead of it, sort of imagine space and time coming down to a point, maybe it's not a point. Maybe it's kind of rounded. Maybe space and time are a little bit more like the surface of the Earth, where the coordinates of space and time aren't straight lines coming together, but they curve. And the whole notion of the very beginning instant of time goes away and just curves around and avoids itself. And you can sidestep this entire notion. It's complex. It's really subtle, complex stuff. But this is what theoretical physicists and cosmologists spend their time doing.
It does sound pretty typical for theoretical physicists and so on to come up with zero as a solution. I mean, mathematicians love zero, right?
Yeah.
Everyone loves zero.
Yeah.
It's so elegant. It feels right, doesn't it?
Yeah.
I'm always a bit skeptical when things come out to be beautiful numbers like that.
But in this case, it would be, I mean, so much of theoretical physics is about elegance, right? And you can push that too far. You can use it as a guiding principle too far to say, this theory must be correct because it's the beautiful ones. Like, the universe doesn't have to be that way. The universe can do whatever it likes. And maybe there's another much more elegant thing that you haven't thought of that the universe kind of likes. But the notion of something from zero is actually really attractive because we actually do see it. You know, you talked about this before. We see it all the time happening around us, right? The universe is constantly borrowing tiny amounts of energy for very small amounts of time in what are called virtual particles, right? In the universe around us, everywhere, all the time, right now, in every tiny little bit of space, there are little pairs of particles, you know, an electron and an anti-electron, popping into existence, borrowing a tiny amount of energy from the universe or from the vacuum, and then almost instantaneously vanishing again by, you know, annihilating each other. And that's happening constantly, all the time across the infinite universe, or at least across the universe as we know it. And maybe, and those are called quantum fluctuations, right? Little wiggles in the quantum universe. And the notion that the Big Bang started with some kind of fluctuation like that there was just nothing, whatever that means. Like, it's not nothing in space and time. It's like nothing.
Yeah.
Borrowed this little bit of energy to make some stuff. And you've got negative energy in the form of gravity there now. And some other mechanism, which goes by the name these days of inflationary cosmology, blew that up in some ridiculous process that increased its size by breathtaking amounts in tiny fractions of a second. And suddenly you've got a universe. But the notion that these quantum processes that are happening all the time could have made the universe is just really tantalizing.
It is. And perhaps there's a link between that zero and the critical density being pretty much the critical density, the density of matter that we observe in the universe today. They're not perhaps disjointed phenomena.
Yeah, I mean, it could be. It could be that the one necessitates the other. That if you are going to have zero overall, then why would it be surprising that everything is really finely balanced? There are theoreticians who spend their entire careers working on that notion of the finely tuned universe. And it's wild stuff.
The one thing about having a zero-sum universe, let's call it, is that you do take away some of the possibilities for the eventual fate of the universe.
Right.
So this is one thing I did skim through when I was writing up my notes for today. So the idea is if you've got a zero-sum universe, all your forms of energy eventually will tend to zero. So your gravitational energy, which is negative, but that will eventually tend towards zero. Your mass density will eventually, as the universe expands, will eventually tend towards zero. Your vacuum energy or dark energy will eventually tend towards zero as your time tends towards infinity. Now, that means that you've taken away, I guess, all the other options of what can happen. You've taken away your big crunch. You certainly can't have that in a zero-sum universe because your gravity would be overcoming the rest of your energy.
Yeah, I guess so. Yeah.
So you're left with your heat death universe. And It's an interesting, I think I probably mentioned it before, I think it's an interesting human psychological phenomena that I don't think we like the idea of a heat death.
It just feels wrong. You know, even the cataclysmic big crunch feels like, well, if you're going to go, do it properly.
But that feels like big crunch universes where and even perhaps a rebounding universe where it goes crunch, bang, crunch, bang, crunch, bang. That feels to many people like a good sort of the way it should be, because it's cyclic. It's we see so many cyclic processes, I guess, in our lives and so on.
Death and rebirth, and it's tied into so many philosophies and theologies.
And it feels sort of like the universe goes on, and that's good and that's fine.
Even if we don't, something will.
Yes.
Yeah.
Whereas heat death is very much. Yeah, well, that's exactly the sound. Yeah,
that's it.
It's everything just rips apart. So you get sort of, instead of 5 protons per cubic meter, you get almost none, and they just sit there in space and feel a bit sad.
Yeah, which is
maybe they decay. I don't know.
Well, I mean, ultimately, there are questions around the ultimate stability of all matter. You know, we think that there are some particles which are stable forever, but asterisk, maybe not.
Maybe not.
In which case, maybe, it all just decays to radiation, which then ultimately, with the expansion of the universe, tends to zero energy as the photons get stretched out to lower and lower and lower frequencies. Nothing.
So, theoretical physicists, cosmologists who are working on the zero energy, just remember that is your universe fate. If you're going to go down that road.
I mean, can I just point out, it's not their fault. Like they're not imposing this on the universe any more than astronomers are imposing anything through their measurements. But it's a fair point that maybe we could just stop thinking about this for a little while until we're a bit more comfortable.
So does that leave us with the answer to the question finally?
Well, I think it does. I think it leaves us with 2 possibilities. It leaves us with the amount of energy in the universe is either a stupendously big number that you could never wrap your head around even if you tried, or literally zero.
Yeah.
And I think you choose whichever one of those makes you more comfortable.
Yeah.
Yeah.
Yeah, exactly.
I think our work here is done.
Could have done it in half an hour. What are we doing?
Well, listeners, if that hasn't put you off the idea of sending in your question to form the basis for an episode of Syzygy, I mean, look, we took what was a very simple question, how much energy is there in the universe? And, I don't know, we somehow ended up at the heat death of the universe. So that's entertaining.
It's always going to happen.
It was always going to happen. Very sad. But listen, if you do want to get in touch, if you've got an idea or a thought or a question or a criticism that has come out of this discussion or anything else that has crossed your path, then you can get in touch with us with a whole bunch of ways. Emily, how do people do that?
Well, you need to go and put your question into the friendly little question box on syzygy.fm, the website.
That's what Eve did, and it worked. Look how well it worked. Brilliantly. Whole episode out of it.
And it's not the first time.
It's not. We probably had about 4 or 5 episodes over the course of the last 100 and something. So you too can do that. Go to syzygy.fm and you can find all sorts of stuff. You can find our past episodes, every episode going back to episode number 1.
Links to the remaining socials.
Exactly. What remains. Instagram, we're on the Instagrams and Facebook and all of those places, as well as a page devoted to our fabulous financial supporters from patreon.com. Go over to patreon.com/syzygypod if you want to become one of those, and you too will get your name on our great cosmic wall of thanks. But look, the main way that you can support the show is just by telling everyone you know about this fabulous thing called Syzygy. They talk about weird stuff like how much energy is there in the universe, and maybe it's actually literally zero. And if people's brains get exploded by that, then they'll enjoy the other things that we talk about too. So spread the word is what I'm saying. But until next time, I guess, Emily, I mean, I'm going to be going away fairly soon.
Yeah, you've got all this work to do in the other hemisphere.
I do. I'm heading down to Australia. I've got some stuff going on down in Sydney. But look, I'm going to take a microphone with me, and you've got a microphone here. And the wonders of modern technology says we should be able to keep doing something. Might not be weekly, but we'll keep going.
Yes.
Good.
Yes.
In that case, we'll catch you next time. See you later, everybody.
See you later.
Bye.